Start.
Hello everyone. In this presentation, we are going to understand how a quadrature encoder interface module in a TIVA microcontroller works. So what you see in the screen is an ENERGIA output of a quadrature encoder interface. So here we are having two columns. The first column is the position of the rotary encoder and the second column is the velocity of the rotary encoder. So the position and the velocity of the rotary encoder can be visualized with the help of quadrature encoder interface module of a TIVA microcontroller, which we are going to demonstrate here in this presentation. So now if you look at the screen, here you can able to see the values are increasing from 20, 30, 40, 50, 100 to 150, 200 in the first column, which is nothing but the position count value. So for example, if you look at here, I am having the rotary encoder in my hand. This is the rotary encoder which is connected to the TIVA microcontroller launchpad, and the output of the TIVA microcontroller launchpad is connected to the laptop, and this output only we are seeing there in the screen. So if you look at here, I am rotating the rotary encoder in the clockwise direction. When I keep on rotating the rotary encoder in the clockwise direction, you can able to see the value goes from 400 to 500, then value goes from 500 to 600 in the first column. In the second column, which is a velocity, where when I stop rotating, right, when I stop rotating, the first column values are also stopped at 738. If you see, the position count value of the rotary encoder is 738, it stops at 738, and the speed or velocity is 0. Okay, so the first column is nothing but the position count value of the rotary encoder. The second column is the velocity of the rotary encoder. Now if you see, soon I start moving this, you can see some changes in the velocity of the encoder. Here if you see, so up to 1000 it counts, then it resets from 1000 to 0. So when I keep on rotating, if you see, when I keep on rotating, we are able to see the velocity values also keep on displaying, right? So when I leave it, you can able to see the velocity value becomes 0, but the position value is something like 583. So when again rotates, there is a velocity value, and after some time velocity value decreases, and 609. It is something like an odometer of a vehicle. So all the vehicles will have an odometer. If you relate this reading with the odometer, the 609 means the vehicle has traveled 609 km and the vehicle has stopped. So the speed is 0. So when I am starting the vehicle and then I keep on moving the vehicle means, so the odometer value is also increasing. That means the number of the distance traveled is also increasing, and the speed value is also getting displayed. After some time, I am going to stop the vehicle. When I am stopping the vehicle means the speed value becomes 0. That means the velocity value becomes 0, and the odometer shows 174 kilometers the vehicle has traveled, something like that. So all the odometer readings and all the speedometer readings are taken from the rotary encoder principle, which is called as wheel speed sensor in an automobile. With the help of the wheel speed sensor only, we can able to measure the displacement as well as the speed of the vehicle. Based on these readings, the braking system works. As we know, ABS belongs to anti-lock braking system and ESP belongs to electronic stability program. So the functioning of ABS, ESP and all speed related or wheel related or mobility related activities in a car is happening only because of the wheel speed sensor. This is one of the way to understand how the wheel speed sensor works, similar to this. So what we have in my hand is something like a rotary encoder knob. All the electronic equipments nowadays you see, we do not have any potentiometer based knobs. If you see the modern washing machines, if you see the modern music players, you are not able to feel the potentiometer experience. You are able to feel something like tick 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 kind of things. So these are all the rotary encoders where there is no wear and tear, and it's very reliable, and there is no need for ADC also. If it is a potentiometer means we need an ADC. So it avoids the ADC value. Why? Because the output of the rotary encoder is the pulses. That is what we are going to experience in this experiments in detail. So coming to this block diagram. So coming to this block diagram, if you see, so this is the TIVA microcontroller block diagram. In this TIVA microcontroller block diagram, as we know, TIVA microcontroller contains ARM Cortex-M4 based processor core inside, and it has a flash memory, and it has an SRAM, and it has a system control peripherals, system control blocks. And if come down, we are having peripherals as groups. There are system peripherals, 6 system peripherals, and there are 5 serial peripherals, and there are 2 analog peripherals, and there are 2 motion control peripherals. So our interest here is to look after the motion control peripherals, whereas we all know the pulse width modulation is helping us to increase the speed and decrease the speed of the vehicle, or increase the speed and decreasing the speed of the motor, or increasing the intensity and decreasing the intensity of the light, or increasing the volume, decreasing the volume of the speaker. So by increasing, the PWM helps in the linear control of an application. If you take up a motor, the motor RPM, let us say the DC motor. So DC motor is rotating in 1000 RPM means, how do we know the DC motor is rotating in 1000 RPM? So to understand, the PWM gives the voltage and the corresponding voltage and current requirement to the motor, and the motor rotates in some RPM. Is the motor rotates in 1000 RPM? That has to be identified. To identify the motor whether it is rotating in 1000 RPM or not, something like this rotary encoder is needed. So this rotary encoder is producing some pulses. This pulse outputs, it produces 2 pulses. These pulses outputs must be given to the quadrature encoder interface module of a TIVA microcontroller. So PWM is going to control the motor, and the quadrature encoder interface is going to measure the speed of the motor. So the motion control peripheral, which includes PWM and QEI module, helps us to make a closed loop control system in a more efficient way. That is the power of the TIVA microcontroller here, which we are experimenting right now. So here if you see in this circuit diagram, so in this diagram here you can see there is a red color is a 5 volt power supply, and this yellow color is nothing but the ground. And if we excluding this red color and this one, means these 2 wires are the 2 pulses, A pulse and B pulse, coming from the rotary encoder, which is connected to the TIVA microcontroller's launchpad things. So VCC ground and pulse A and pulse B. So why pulse A and pulse B? Why we need 2 pulses from the rotary encoder, which is connected to the quadrature encoder interfacing? That is what we are going to experience here. So when you look at this block diagram, so here you can see the closed loop DC motor control using TIVA microcontroller. This is the motion control peripheral of the TIVA microcontroller, just now as we have seen. So pulse width modulation. So PWM output must be given to the H-bridge motor driver, and the H-bridge motor driver output is connected to the motor. In the motor shaft, we are connecting the rotary encoder. So rotary encoder, this is the rotary encoder. This knob is connected to the motor shaft. So when this rotates along with the armature of the motor, and we will get the 2 pulses, and in the name of phase A, pulse A as well as pulse B. So the A pulse and B pulse must be connected to the quadrature encoder interfacing, which helps us to measure the speed of the motor and the position of the motor and much more. Okay, so the presence of this motion control peripherals in TIVA microcontroller helps us to form a closed loop control system. So why two pulses? This is very important. Why 2 pulses? This is very important. To understand this, these are all the 2 pulses which is coming out from the rotary encoder. So whenever you see here, if the motor rotates, when you give the pulse width modulation, the motor will rotate, it will produce as a pulses. So the pulses will come from the rotary encoder, and there is a counter. The quadrature encoder will have a counter, it will count. But counting means one pulse equal to 1 meter means 100 pulses means 100 meter it has crossed, 1000 pulses means 1000 meter it has crossed, so 1 kilometer it has crossed, something like that we can say. But if the motor is rotating in opposite direction, means the opposite direction also we will get the pulse. So, with the help of one pulse, it is very difficult for us to, or it is impossible for us to find out the direction of rotation. This is the very important point we have to understand. So if there is only one pulse can help us to measure the displacement as well as the speed, but in which direction it is rotating, that cannot be understood with the help of one pulse. So the second pulse, that is A and B, both pulses are here available only to find out the direction of rotation of the motor. Beyond that, there is no need for 2 pulses. That is what we are going to experiment it here. Okay, so there are 2 pulses. So you can see pulse output from the rotary encoder for clockwise rotation. So when we rotate in the clockwise, so you can see the pulse A will go from 0 to 1 first, then pulse B will go from 0 to 1, and then this maintains the 90-degree phase differences like this. So whenever the A pulse goes from 0 to 1 first, and then B pulse goes from 0 to 1 next, then that justifies the rotary is rotating in clockwise direction. But when you rotate in anti-clockwise direction, the B pulse will go from 0 to 1 first, and then A pulse will go from 0 to 1. So whenever the B pulse goes from 0 to 1 first, then A pulse goes from 0 to 1 next, means that justifies the motor is rotating in anti-clockwise direction. So the direction of rotation can be identified one and only through these A pulse and B pulse. Hence, for an application, if you want to measure the direction of rotation, means it is mandatory for us to have two pulses A and B from the rotary encoder, and from this rotary encoder, which is connected to the motor shaft, we are connecting it to the TIVA microcontroller launchpad, which is what is A0 means? There are two quadrature encoder interfacing. So A pulse of 0 QEI, B pulse of 0 QEI, which is connected to this pulses. So why we need to find out the direction of rotation, means there are so many things which we can understand. If you say, for example, so many applications, if you look at the lift door, when the lift two door lifts, means when the door closes, means the count increments from 0 to 100 in clockwise direction. Then when the lift door has to open, means from 100 to 0 it can decrement the count. So finding the position of the door with the help of rotary encoder will help us to close the door efficiently and open the door efficiently. When there is an arm which is picking in place, means pick it at 0 position, placing it 100th position, and coming back from 100th position to 0th position, and then pick from 0 position to 100 position you can place. So everywhere there is a need for clockwise and anti-clockwise rotation, and it is mandatory for us to measure the clockwise and anti-clockwise rotation. For measuring whether the motor is rotating in clockwise or anti-clockwise, we are in need of rotary encoder, which should produce two pulses. That is what clearly given. So this A pulse from the rotary encoder is connected to the 33rd pin of this TIVA launchpad, and the B pulse is connected to the 32nd pin of TIVA launchpad, which is an alternate function of parallel port D6 and D7 of the TIVA microcontroller, which has a pin number of 53 and 10 of the TIVA microcontroller, which we can see in the launchpad diagram. So the TIVA microcontroller launchpad, if you see, this is the TIVA microcontroller launchpad. In this TIVA microcontroller launchpad, here if we see, so there is a PD6 pin number 33. PD6 pin number 33's alternate function is PA0, phase A0, and you can see here PF1's 30th pin is phase B0. So A0 and B0 is available in the launchpad here, but there is a possibility for us to make PD7 as a phase B0. Why? Because if you see the diagram, if you see this data sheet, the pin multiplexing features, as we know very well, there are two pins which can be multiplexed. Here you can see the phase A0 and phase P0. Phase A0 can be either PD6 or PF0. Phase B0 can be either PD7 or PF1. So in the launchpad, PF1 is shown, but we have connected to PD7 for convenience. That's all. So PD6 is for phase 0 and PD7 is for phase B0, phase A0. There are two pulses. So A pulse and B pulse. A pulse from the rotary encoder must be connected to PD6. B pulse from the rotary encoder is connected to PD7 of the microcontroller. In the launchpad, this PD6 and PD7 of this microcontroller is connected to 34th and 33rd pin, 33 and 34th pin, which is 33 and 32th pin. 33 is PHA0 and 32 is PD7, which is PHB0. That is what you are able to see here. Here if you see, this is 33rd pin and 32nd pin, which is phase A pulse and phase B pulse of this rotary encoder. So we are supposed to know what is phase A and phase B of this rotary encoder. Only if we know what is this rotary encoder, what is phase A and phase B means, if you look at the diagram of this rotary encoder, you can understand much better. This is the 5 knobs, this 5 terminals of this rotary encoder, what you are able to see here. So here you can see the pin A, encoder pin A, B. So these 2 pins, this A and B, these 2 pins are connected to this phase A and phase B pin of the quadrature encoder interfacing module of the rotary encoder. So this is the rotary encoder part, datasheet of the rotary encoder which we are using, which is the rotary encoder knob. So all our washing machines, all our refrigerator knobs, all our micro oven knobs, all our music system knobs, all the oscilloscope knobs, all the function generator knobs are mostly rotary encoder based. Why? Because it replaces the potentiometer based encoder, potentiometer based knob systems, which is very old, and this is very more accurate and more it is programmable, and the output is only pulses as we see here, and it is very comfortable to integrate with the digital systems as we know very well. So that is the idea here. So now we have seen everything, how best it works, and coming to the coding part. This is very interesting, and as we all know, ENERGIA is very user friendly environment for us to experiment all the higher end microcontrollers like TIVA Microcontroller. So the code for this is very simple. Here we are including the standard interrupt header file and system control header file of the TIVA Microcontroller. And because we are interfacing quadrature encoder interfacing block of the TIVA Microcontroller, so 3 files has been included, and we are interested to see the output in the serial window. So serial window has been initialized, and you are setting up the quadrature encoder interfacing module by using the system control peripheral enable function. System control peripheral enable quadrature encoder interfacing 0 is initialized, and we are configuring the PD6 into phase A0 and the PD7 into phase 0. So the general purpose input outputs alternate function PHB0. For that we are configuring the map. We are mapping the GPIO into phase A0 of QEI. We are mapping the GPIO PD7 into PHB0 of the quadrature encoder interfacing, and then those pin 6 and pin 7 are PD6 and PD7 of this particular quadrature encoder interfacing, and we are enabling the quadrature encoder interfacing by using the corresponding registers by QEI, quadrature encoder interfacing configuration registers, by using the necessary functions. And then we are initializing the quadrature encoder interfacing velocity. So we are configuring the velocity register with the corresponding values, and then we are enabling the quadrature encoder interfacing pulse counter, and we are enabling the quadrature encoder interfacing velocity. So pulse counter, which is an odometer, and velocity, which is a speedometer, something like that we have managed. So the initialization is being done in the loop. Then in the setup we have initialized, and in the loop if you see serial print. So you are printing the position. So you are getting the position and then you are displaying, and then comma, we are getting the velocity and then displaying. So that's all. So with the delay of 100. So this is what keep on happening. So once after you download it, so after downloading this, downloading into the TIVA microcontroller, and we can able to see, visualize it. Here able to see velocity is also 0. Sorry, the position is also 0. The velocity is also 0. When I start rotating, as you see, when I start rotating, the position is also increasing, the velocity is also increasing. When I leave it, the velocity will become 0. The vehicle has stopped, but it has traveled 162 kilometers, something like that you can say. So the presence of quadrature encoder interfacing, and by initializing this, we can very well get the position and velocity and much more. Right now we are able to see only this values. Okay, so to know much more, let us go to the quadrature encoder interface module in the data sheet, which is quite interesting. Quadrature encoder interfacing in the data sheet. It is very interesting. So we can go to the QEI module in the data sheet. So here you can see this is the general block diagram of the quadrature encoder interfacing. Here you can see this rotary encoder, the 2 phases, phase A and phase B, 2 pulses are coming from the rotary encoder, where the quadrature encoder, this is very important, this quadrature encoder converts these 2 pulses into the clocks as well as the direction value and the velocity value. So there are registers in the quadrature encoder interfacing. There is a position integrator which contains quadrature encoder position value and then quadrature encoder maximum position register, and there is a quadrature encoder interfacing speed value and the speed count register. So we are reading these two values and then we are displaying it in the screen. So the two pulses, the quadrature encoder, what it does is converts into the direction pulse as well as the clock pulse, which we are going to see now in the data sheet. Go to the data sheet. In the data sheet you can understand how this quadrature encoder interfacing works. Go to the data sheet, go to the quadrature encoder interfacing chapter. In that chapter you can able to understand very well how this works. Here if you see, so in the data sheet if you go to the 21st chapter is quadrature encoder interfacing. In this 21st chapter the features has been given as we all understand, we know that. If you go to the diagram, so this is the diagram which you have seen now. Here the signal description if you see, this is very interesting, right? So the phase A and phase B, see quadrature encoder and velocity pre-divider operation. This is very important. If you go to the PPT here, so the quadrature encoder, two pulses, phase A, phase B from the rotary encoder is coming as an input. It is converted into clock pulses and the direction pulses. That is what you are able to see in the data sheet here clearly. Just look at the data sheet. Here you can see phase A and phase B. So what is the clock? Now you can know quadrature encoder interfacing. Quad means what? 4. So there are 2 rising edges and 2 falling edges in the 2 pulses. For every rising edge, the quadrature encoder produces 1 pulse. Here you can see phase B goes from 0 to 1, there is 1 pulse. Here phase A goes from 0 to 1, there is 1 pulse. Phase B goes from 1 to 0, there is 1 pulse. Phase A goes from 1 to 0, 1 pulse. So for one, there are 4 pulses you are getting for one particular position rotation because of these 2 pulses, hence it is called as quadrature. So quadrature encoder gets the phase A and phase B pulse and it produces the 4 pulses continuously as you see here. So now at this point, you see at this point if you are changing the direction means, so here you see phase B goes from 0 to 1, then A goes from 0 to 1, B goes from 0 to 1, A goes from 0 to next means, let us say this is the clockwise direction means, now if you see A goes from 0 to 1 and then B goes from 0 to 1. Next. So here B goes from 0 to 1, A goes from 0 to 1, hence it is clockwise direction means, here A goes from 0 to 1 and B goes from 0 to 1 means it is anti-clockwise. So direction has changed. So this is the primary requirement for us. So if A goes from 0 to 1, then B goes from 0 to 1, it is some other direction. B goes from 0 to 1 and A goes from 0 to 1 means which is understood by the direction register. So up to here B goes from 0 to 1 first, hence it is rotating in one direction. The direction register direction bit is logic 1. When we change the direction of the rotation means the pulses changes and this direction bit also changes. So when it is 0 means, when the direction bit is 0, it denotes the motor is rotating in anti-clockwise direction. When this bit is 1 means it denotes the motor is rotating in clockwise direction. How do you know the motor is rotating in clockwise direction or anti-clockwise direction? By looking at the rising edge of the 2 pulses. If the B pulse rising edge first, then A pulse rising edge means clockwise. A pulse rising edge 1 and B pulse 1 means anti-clockwise. Again here you can see A pulse 1, B pulse 1 anti-clockwise. Again you see direction changes. Again A0 to 1 first, B0 to 1. Here again you see again direction changes. B goes from 0 to 1 first and then A goes from 0 to 1. Something like that it goes on. So these are all the 3 pulses. So the clock divider. So here clock divider, what is this clock divider? If you go to the block diagram in this, so the divider means it is a prescaler as we know. This is the clock divider. So the 4 pulses divide by 4. So the input frequency is divided by 4 and then it is counted here. So this is divided by 4. So the clock divider output. So here you will see direction pulse, clock pulse and the clock divider output. So clock divider output is this pulse. As you see in the data sheet here, this is the divided by 4. So 4 pulses means 1 pulse, another 4 pulse means 1 pulse. So this is how the quadrature encoded block diagram. So from these 2 pulses, there is a possibility for us to find out the position, there is a possibility for us to find out the speed, and there is a possibility for us to measure all other parameters of a particular motor. And there is another index point where we can able to fix the starting point. Okay, so there is one particular button here So it can rotate in clockwise or anti-clockwise, and there is a button here. So there is a possibility for us to press. So the center pin can be connected to the index pin. So that index can cover as an input here, which is nothing but the 0 point. Fixing the 0th point is done by just index register like this. So if you go on like this, there is a possibility for us to make a wonderful closed loop control system which can be applicable for any motor based applications, any DC motor based applications. And finally, coming to the output once again. So here you see now the vehicle is traveling in the clockwise direction, so it is keep on incrementing. Now I am rotating in clockwise direction, it is keep on incrementing. When I stopped, 0. Now I am rotating in anti-clockwise direction. Now it is 700 means if I rotate in anti-clockwise direction, it should become 600. Yes, it is becoming 600. So velocity changes in the opposite direction, 400, 300, 200 anti-clockwise, and it stops means velocity 0. So in clockwise 300, 400, 500, anti-clockwise 600 to 500, 400. How it is able to display 300, 400, 500 while rotating clockwise, 500, 400 anti-clockwise means because of these two pulses coming from this. So finally, the quadrature encode interfacing module. So the quadrature encode interfacing module in a TIVA microcontroller helps us to measure the direction of the rotation and the speed of the vehicle. Where the speed and the direction is happening? In the motor. Who is controlling the motor? PWM is controlling the motor, as we see here in this. So this motion, hence that is why it is called as motion control peripheral. So the motion is controlled, and in a closed loop we are able to monitor the measured speed. Say for example, motor has to rotate in 1000 RPM means we can measure whether it is rotating in 1000 RPM or not with the help of rotary encoder. If the speed is 900 RPM means you can increase the pulse width to reach up to 1000 RPM. If the speed is 1200 means you can decrease the pulse width to bring back to 1000 RPM. This is what I am talking about, the closed loop control system. Whether it is rotating in 900 RPM or 1200 RPM, which can be measured only with the help of rotary encoder, which is connected to the shaft of the motor. And the output of the rotary encoder must be connected to the quadrature encoder interfacing to make a wonderful closed loop control system for any motor control applications. Thank you.